Hey everybody, wanted to come back and talk about polynomial functions, but here specifically about graphing them, and I'll show you a couple tricks, all right? First of all, I should mention that polynomial functions have two uh, things on them that they have to have. They should be continuous and they should be smooth. So these two on the left that you see, they are both continuous and smooth. If I were riding this like a train track, roller coaster or something, the roller coaster goes down, it comes back up. There's no holes, there's no gaps, there's no sharp turns. Everything is A, continuous, and B, smooth. Same thing for this guy here. There's no holes in the track. I'm not going to fall. I'm not going to get jerked around too bad. It's pretty steep, but I don't like roller coasters. But you get the idea, right? When we look at this one, though, the absolute value function that we've studied before, bonk. See how it has a problem right there, and that would not be smooth. Okay, so that is not a polynomial function. Furthermore, this one right here, there's a hole in the track, and your roller coaster is going to fall. That is not continuous. So just kind of throwing a couple terms out there that are worth kind of thinking about there, and that's not what we want. All right. But we're talking about polynomials, so um, hopefully that's not even an issue. Okay. So let's once we've got that figured out, finding the x-intercepts solutions by factoring. We have factored things before, but we haven't factored things where it's x to the sixth power. But the tricks are the same, the strategies are the same. And if you remember, whenever we're looking for roots, the first thing that we want to do is take our function and just write it as an algebraic expression that is set equal to zero. It's handy to have this equal to zero because, again, we could think about this as the y value, the functional value, whatever's coming out of the function, and where that's equal to zero would be right on the x-axis. So just set that equal to zero. We've done that before. When I look at this thing and I think about factoring it, you remember the first trick in factoring was look for common factors, right? Is there something that I can pull out of each pile and make each of the terms a little bit smaller, simpler, and everything? And I think you can see I could get an x squared out of all three of those. So that would be the first thing that I would do, pull an x squared out and then figure out what the three terms in here that I could distribute x squared to get x to the sixth. Well, that would be x to the fourth. Remember power to a power, not power to a power. When we're multiplying bases, we add the exponents. So 2 times 4, 2 plus 4 would be 6 there. Right here, I need a minus 3. I need two more x's, so I'll put that. And then finally, I'll have a 2 right there. Think about distributing that back and see if that won't get you the original function. Okay, with that out of the way, things look a little bit better. There's still x to the fourth, but that is a perfect square, so maybe I can get away with doing x squared times x squared. Worth a try, right? Let's look at the back here. I need two numbers that multiply to 2, and I see that the signs are going to be the same, therefore both negative, and I'm going, well, 2 and 1 multiply to 2 and add to 3. So, let's try that. If the signs are the same and negative, I'd put a negative here and a negative here. Double checking that, x squared times x squared would be x to the fourth. Outer, I'd have 1 or negative 1 x squared. Inner times the inner negative 2x squared together, that's going to give me the negative 3x squared. Negative 2 times negative 1 would be positive 2. So we haven't messed this thing up yet. We're also not done. And so let's keep going with it. Both of these can be factored. This one right here would be a difference of two squares if 2 is a perfect square. It's not, but you know what we can do? I could write it as x plus the square root of 2, x minus the square root of 2. Now, I didn't get an integer there, but that will work. And x times x would be x squared for the first times first. Outer would give me negative 2, negative square root of 2x right here. And this would give me positive square root 2x. Those are going to cancel, those cross terms. And when I do the last times the last, then I'd have square root of 2 times square root of 2 is 2. And a positive times a negative would give me the 2. So that checks out right there. Perfectly good factorization. And we could do a similar thing back here on the back, except that it already is perfect square. So we don't have to mess with those square roots. We could just write this one out as x plus 1, x minus 1, like that. Okay? Since we have this thing set equal to 0, like that, I am now multiplying x squared times this, times that, times that, times that. I'm multiplying 5 or even 6 things there and getting 0. I need to set each of them equal to 0. So one thing you may want to do here, I mean, this x squared, I really could write that x times x, couldn't I? There's really two x's there. So I could set that first x equal to 0. I could set the second x equal to 0. And those are two solutions of my polynomial. Okay. Moving on to this one right here. I need x plus square root of 2 equal to 0. So that would mean that x equals negative square root of 2. Just subtract square root of 2 from both sides. There's our third root. Third solution, we'll take the next term there, x minus square root 2 equals 0, add square root of 2. There's number 4. How many are we looking for? Remember, highest power right there, the degree of the polynomial tells us how many we can have. I've already got 4, and I've still got 2 more back here, so it looks like we're right on track to get all 6 of them. I'm going to skip down here so that we can not cover up the graph there, but that would suggest that x minus 1 is a root, and this last guy here, x minus 1 equals 0, means that x would be equal to 0. Those are the 6 roots that we were looking for. We got 6 real solutions to this polynomial, and they're all there. We can graph them now, and that would look like this. We've got the first one is at 0. And here, there it is. Look at all that. Okay. Uh, so there's the first one at 0. The second one at 0 is right smack on top of it. So we'll put that there. Negative square root of 2. The square root of 2, a decimal approximation is like 1.414, right? So I'm going to come back here, negative 1.414, and put a dot right there. And now we've gotten this guy and this guy and this guy. We need the positive square root of 2. So I'll come over here and put a dot. Takes care of this one. I also have negative 1, which would be right here, and positive 1, which would be right there. All right, so there's a whole lot going on, but we know the 6 places where it crosses or touches the x-axis. Right? And that pretty much nails down what we're trying to do here. I'm going to look and see what this should be. I've got an even number. X to the sixth is my biggest term, right? That's the degree of this thing, the order of 6 right there. And so I know I'm looking at a parabola with some stuff going on in the middle. And I see that the coefficient of that x squared is positive. So this is a bowl up parabola. So I can come in here and where am I? Oh, there I am. Okay. Dang. I realized I'm on my little bitty computer screen. All right, let's try to get where to go. There it is. There it is. Okay. So we need to come, here's that bowl going up. And here's the bowl going up on this side. That's that in behavior right there. And I don't know that I did a great job on that, but you get the idea, right? It crosses the x-axis right there. It's going to come back up. How far down does it go? I don't really know. We could find out though. We could pick some numbers between -1 and -2, plug those into our polynomial and see how far down that goes. I'm going to just draw it like that. It comes back up. It comes down and it's actually touches right there. And so it's doing something like that. Again, those between -1 and negative square root 2, it may go way down. But that's the general behavior of this thing. And I'm going to tell you, why that works. Um, I didn't get my calculator out. Let me go find that real quick. And let's see what it's showing this thing as. When I put in that function right there of x to the sixth minus 3x to the fourth plus 2x squared and graph that, there it's coming down, and you can see that there's a whole lot going on in the middle there. It didn't go down very far at all, did it? So maybe my picture's not that bad. Let's zoom in a little bit here. I'm going to set the window up. If we went between -3 maybe and +3, and X scale, that's fine right there. And let's zoom in a little bit. Didn't change the y-axis. Okay, maybe even a little bit more. Let's change the y-axis too. Let's go down to let's say -2 to +2, something like that. Not 22. Let's go to 3 just in case. All right. So here that thing comes down, bloop, and see how it bounced off the x-axis right there at the origin and went back up. And you're probably asking, how did he know that it bounced right there, that it didn't cross? And the answer to that is something we want to talk about today. The short answer here is that we had two zeros. And whenever you see a double root like that, then you know that um, when you see these two zeros right here, that double root says that that's a bounce. Okay, it didn't cross right there. It just came down and touched the x-axis. It's almost like there's a little parabola right there on the thing. If I were to zoom in right there at the origin, we might mistake that for a parabola, right? Well, when you've got that x squared right there at the origin, that's one of those. One of the things we want to see this time, and I've got a better example here for you, more stuff. Anyway, here's another example. Let's give this one a try, and get this guy out of the way. Again, factoring is probably your best bet on these. Oh, this one's a weird one, right? I can't pull anything out of all four terms. What am I going to do? Maybe grouping. Remember factoring by grouping? If I just come in here and split that thing like that, I could pull an x squared out of the first two, and then I would need an x minus 5 to get back to where I was. Check it out. X squared times x would give me the x cubed. X times -5 gives me the -5x squared. And so I've got that part right there. Now, back here, I have a -x plus 5. And look at right there's an x minus 5. If I could make that look like what I have, what I could do here is factor out a -1 like this. -1 times something to give me -x. Oh, I need an x, right? And that would work. I need something right here times -1 to give me +5. And if I had a -5, that would do that, right? -1 times x is going to be -x. -1 times -5 is a +5. Okay. And all of that wrangling there just meant that I do have something in common. This x minus 5 is now common to both of those terms. So I can pull him up front. And then what would I need? Here's an x squared minus 1. And if I were to multiply x minus 5, distribute that into the x squared minus 1, I'd get back to where I started from. Finally, keep trying to crack this nut down into smaller and smaller pieces. Can't really do anything with the x minus 5, but I've got a difference of 2 squares there in the second binomial. So we will factor that again and get an x plus 1, x minus 1 like that. All of these are equal to 0, when I multiply, because we're looking for the roots again. So I'm going to get 3 roots this time. I'm multiplying 3 things, getting 0. Not surprising because that's the degree of this thing. If I take the x minus 5 equals 0, that means that x equals positive 5 is a solution. It's a root, and I could put a little dot right there. That's one of the places that this thing crosses or touches the x-axis. I take the second one right here, x plus 1 equals 0, so I get a root at x equals negative 1 right here. And then lastly, x minus 1 equals 0 would mean that x equals positive 1 is the thing there. All right. Got to work out what the general shape of this thing. So I go back to my polynomial and I say the highest degree, the order of this is a cubic function, right? And so I know that when I put a negative number in and cube it, I'm going to get a negative number. This thing's coming up out of the basement like this. It's going to go up over here. And so this thing has to come up and back down like that. And that would be the graph of this thing. We'll confirm that with the calculator, but if I can find, there we go. And um, and I've got that weird scale, so I may have to change that up here. But here is x cubed minus 5x squared minus x, and then plus 5. And we graph, and you can see some of it there. Let's go to Zoom Standard. And I didn't go down quite far enough, but you can get the idea, right? That we've got the basic shape. And I didn't go high enough either. How would you find out how high to go and how low to go? Well, the height there, that looks suspiciously like the y-intercept, right? So that would be pretty easy to find out, and it would certainly give us a better feel for where this thing is going. So that would be worth your while. All you have to do is plug in x equals 0, and so that wipes out everything. I'd have 0 cubed minus 5 times 0 squared minus 0 plus 5. Only thing left is that plus 5. So really, that gives me a dot up here, and this thing should come way up like that and down. If I'm only interested in the roots, I don't really care about the y-intercept, you know, but it's kind of nice to know. How would I find the bottom of this thing? How far down it goes? If it were me, I would go, this dot is at 1 and that one's at 5. So in the middle is 3. And I'd check that point. So, use x equals 3. And when I put in here 3 cubed minus 5 times 3 squared minus 3 plus 5, that'll give me another data point down here somewhere. 3 cubed is 27, minus 5 times 9 would be 45, minus 3 plus 5. Big mess. 27 minus 45 would be negative 18, negative 21, positive 16, negative 16. I don't even know. Why am I trying? Why am I stretching this thing? I don't need a calculator that big. Come on. So 27 minus 45 minus 3 plus 5, negative 16. Okay. And that's off the graph. So I'm not going to even get there anyway, but this thing would go on down, down, down. And so real quick, you can get a pretty good idea of what this thing is going for. We're certainly interested in the end behavior, and because that's a positive coefficient with a third power, we know it's coming up from negative infinity. It's going to do some stuff here in the middle and go back up to positive infinity there. Just keep climbing, 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 climbing. Um, and then we know where it crosses the x-axis. That's important because these are the solutions that we would be looking for if we were trying to solve this for some kind of practical application. Okay. You want to try it the other way? What if we had the graph? Could we build the equation? Huh. Well, I see that there is a root right here at x equals 1. I see there's a root right here at x equals -2. And there's a root back here at x equals -3. So if I kind of do that thing we did before, but backwards, if I subtract 1 from both sides, this would be a 0. If I add 2 to both sides, I get a 0. And right here, add 3 to both sides like that. So these are the three pieces. Before we had this and we turned it into that. Well, if I'm going backwards, I need to go the other way. So what I've got here is a polynomial where there's an x minus 1 and an x plus 2 and an x plus 3. And we're setting that equal to 0 to find the roots, but we started with the roots, so we're going backwards here. We could name this function anything we want, h of x equals that. Nothing wrong with it in that form right there. But we may want to express it as a polynomial and get it in descending order. So I would FOIL these two right here. You'll have first times the first would be x squared. Outer would be a 2x minus 1x for the inner would be a plus x. And then -1 times +2 would be -2. So there's the foiling of those first two. Haven't touched this thing on the back yet, so I need to put him in there, and we're going to take each of these three terms and multiply it by each of these two terms. So I'm going to take that x squared times the first one back there, x would be x cubed, and the x squared times the 3 would be 3x squared. So we multiplied this guy times both of the things in the second one. Now I need to move on and get this one. The x times x is going to be an x squared. X times 3 is a 3x. And he did his thing. And now that -2 times both of those would be -2x minus 6 like that. At this point, we're looking for common terms to combine. There's some x squareds and here's some x's. So just cleaning up at this point, x cubed, I got +3 of them, and +1 would be +4 x squared. Putting those x terms together, 3x minus 2x would be plus x, and then a minus 6. And that would be how you would want to get the h of x right there with the thing. Okay. And you can see the order is 3, and we had 3 roots, and it's a cubic, and that has the basic cubic function to it, down from below up to above. And so that looks good. Um, now, here's where we need to talk about the multiplicity of zeros. How many zeros do we have at a point? Remember that one where it was x equals 0 and also x equals 0? It was doubled up in there. That's what we're talking about. How many times do you get a 0 right there? And there are three options illustrated here. You could have more, but they would start to kind of fall into the same category. Um, if you have a single 0, okay, and when I'm looking up here at this polynomial that they've done there, see how the x plus 3 there's only one x plus 3, whereas right here, x minus 2 gets squared. So there are two of those. And then lastly, right here, x plus 1 gets raised to the third power. So I've got three of those. The roots on those, when I set this equal to 0, I'd have x plus 3 equals 0, so x equals negative 3. And sure enough, there's a dot there at x equals negative 3. All right. When I take the second one, the x minus 2, it is squared. I set it equal to 0. I can kind of forget about the squared for a second. And I'm going to get a root at x equals positive 2, being this dot right there. And but because of the squared, that happens twice. The multiplicity right there is 2. Sometimes you'll see them use the letter P to represent the multiplicity. Not really sure why. But for the x plus 3, p equals 1. That root only happens once. For x equals 2, the multiplicity p is equal to 2 because I get it twice there. That squared means I got to take the first one, I got to take the second one, and I get the same thing again, right? When I do x plus 1 to the third, that's really x plus 1 times x plus 1 times x plus 1. And you could see that I'm going to get a root of x equals negative 1, 1, 2, 3 times. Okay? So that's the multiplicity, would be 3 there. Here's what you got to do. Whenever you have a multiplicity of 1, like the negative 3, then the behavior of the line at that root is going to look like you have x to the first power. Okay, y equals, some constants, whatever, but x to the first power. That's a straight line. So that's a place where the graph crosses the x-axis. All right. Whenever you have a multiplicity of 2, that's kind of like y equals x squared, which is going to give you a parabola. And it comes down and just kisses it right there, just touches that the x-axis and goes right back up, just like a parabola would. Touch x-axis doesn't cross. Okay. And then lastly here, the last one they do is what if your multiplicity is 3? Then it's going to look like a cubic function as if you had y equals x cubed. And in that localized region, in our case, that was the one where, um, over here at negative 1. So if you look at negative 1, see how it looks like a cubic? If you kind of zoom in, draw a little window around there, there's a little cubic right here where there was 1, multiplicity of 1. I've got a straight line. This was a multiplicity of 3, so it looks like a cubic function. Right here, I had it twice. P equals 2, P equals 2. I'm sorry, x equals 2, x equals 2, so it's there twice, multiplicity equals 2. It looks like a little parabola. And if you zoom in right there at that point, draw a little window around it, then you're going to see a straight line or a parabola or a cubic function, depending on your multiplicity. So that's kind of a nifty thing, I think, right there. Here's one more of those. We could do this again, and let's see if we can shortcut this a little bit. Right there is one. So that would be x equals negative 3 is one of my roots. How many of those do I have? Well, in that region, it comes down, touches, and goes right back up. It does not cross. So I know the multiplicity is 2. When I set that equal to 0 well, no, I'm sorry, when I get 0 on one side, I need to add 3 to both sides. So that would be an x plus 3. And I know it's there twice, so I need to put a squared in there. That's part of my polynomial. So when I'm building this polynomial, h of x, I know there's an x plus 3 squared to reflect that little where it comes down and bounces off that. All right. The next one that I have, we'll go to red here, I guess, just for something different. Right there is 1. That's at x equals -1. So I need to consider that one. X equals -1. I get a 0 on one side. I need to add 1 to both sides right there. That's part of my thing. So x plus 1 belongs in my polynomial. But notice right here when I window it, it's just a nice straight line right there. It crosses and goes on and does its thing right there. That tells me for sure that the um, multiplicity is 1. So I only need that one in there once. I've got one more root over here at, looks like it's right at 4. And I kind of zoom in right there. I think what kind of functions that look like? Comes up from the bottom, flattens out, goes back up. Oh yeah, that's a cubic. So I know that there is a multiplicity of 3 at x equals 4. And if I subtract 4 from both sides, then I'll have x minus 4 equals 0. So the last contributing factor here would be x minus 4. And I got to have it in there 3 times to get that little cubic function going on. That would be my function right there. I don't know that we need to multiply that thing out. Knock yourself out if you want. I'm going to leave it right there. But you could see how it would go um, to the you know, you could figure out if you had a sheet and a half paper, you could figure out what all that is, right? What would my degree of that thing be? Well, I can kind of come in here and say I've got 2 x's right there. I've got 1 right here, and I've got 3 right here. So that would be a total of 6. All right. I also could just add the total multiplicities there and get 6. Okay. So that would work. There could be more, right? I could have some complex roots, but it's at least a 6. So let's leave it like that. We've done this, a couple times now. The in behavior. This is nice to know because that's telling me what's going on. I've got some names I use for it. I don't know of anything else. Am Huh, lost it. I don't think I'm even, oh, I'm not even writing this. Oh, there we go. Okay. Sorry about that. We have seen that even functions with a positive leading coefficient go up on both sides, right? Whatever they do in the middle. We have seen that negative coefficients uh, for even functions are going to go down on both sides, the inverted parabola there. I'm calling that a bowl. So this is kind of bowl up and this would be bowl down. There's probably a better name for that, but it works. Whatever. Okay. Over here, meanwhile, we know with odd degrees like cubics, like fifths, sevenths, ninths, whatever, that it's going to be down on one side right here. Obviously, if I cube a negative number, that'd be a negative times a negative times a negative would give me a negative. So I'm down here, and a positive times a positive times a positive. I'm going to get bigger and bigger on this side. I kind of connect the line here and call that the snake. So, you may hear me talk about snake up and snake down over here. But Again, I'm sure there's a better word for it. Okay. When you're in physics, you can make up words anytime you want. Okay. So there you go. The turning points, I mentioned this at the end of last time, and we talked about minimums and maximums a little bit. So you can see that this thing bottoms out right there, and then it goes up, 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 and then it stops going up right here and starts going back down, and then it goes down for a while and has another minimum right there. So I got a couple minimums and I got a maximum here, a local maximum. I zoom in. Obviously, it's not a total maximum because these things keep going up and up, right? But, in a little region right there, uh, if I draw a little window right there, that would be a maximum in that window. Okay. So there's a little bit down here at the bottom. This came out of the book. I know it's a little bitty. I'll read it to you here if you can't read it yourself. A turning point is a point on the graph where the graph changes from increasing to decreasing. So rising to falling or decreasing to increasing. Okay. So all they're saying right there is that here we're going down and then we start going up. So necessarily there is a turning point there, and that would be a minimum. Or maybe we're going up and we start going down. That would be a maximum right there. But in any case, there are turning points on that thing. We also mentioned that right here it's bowl up and right here's bowl down. So there's somewhere in here a point that they don't name on here, but that would be that inflection point where it changes from bowl up to bowl down or vice versa, inflection point. La la la. Okay. Here's a couple more little bitty notes. Given a polynomial function, sketch the graph. These are the steps that they use here to kind of go through and do this. Um, First up, you want to find the intercepts. The X and the Y intercepts would help you, right? So we'll kind of make a little note right there, X and Y. If you knew where all the X-intercepts, all the roots and where the Y-intercept was, then like the ones that you've seen me do here, that kind of nails it down pretty tight, right? Check for symmetry. And here they're thinking, is it an even function or an odd function? And we already know about that. Is it, x squared, x to the fourth, x to the sixth is both up. So that's our end behavior. Think about what that's doing. Behavior. Okay, use the multiplicities to determine the behavior. Um, and there again, if x equals one, or if p equals one, shoot, p equals one, it's going to look like a straight line crossing, could be going down, could be going up, whatever, but it's going to cross that x-axis in one point. If it's p equals two, then it looks like a parabola and it comes down and touches it. P equals three, I missed it. Boop, that's a little better. P equals three. Now I'm going to get a snake going on, something like that. All right. Use in behavior. Yeah, what we just did. All right. This is summary. If you have the graph, and we did some of these too, then identify the x-intercepts. We did that. We had to get the roots. Here it looks like it's crossing at one half, negative one half. So, if I set x equals negative one half, that would mean that x plus one half equals zero. And I want that to go into my polynomial right there. And, and we're putting that in and building that thing little by little. Last little thing down there at the bottom is called the intermediate value theorem. And a theorem means it can be proved. I'm not going to prove it here for you, but these theorems are important in math because we kind of build structures, if you will. Well, if this is true, then that and that and that have to be true, which means this other thing. And we're kind of building a little tower out of our rules, and that whole tower supports, it is the structure of mathematics. So, on a totally different layer of math here. There's a whole lot of theory and stuff, and this theorem is one of those things. Let f be a polynomial function. Okay. So it could be any polynomial function that you could think of. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between them for which f of c equals 0. Huh? Let me draw you a picture here. If I can find my righty thing again. There we go. Okay, that's a pretty good place too. What they're saying is if this is the x and the y axis and you have a function f, and at some point f of x gives you a positive number and you're up here above the x-axis, and then somewhere else later on, before, it doesn't matter, some other point you get a negative number out of this function. Well, remember that functions are continuous and smooth, so necessarily there's some point in there where f of x equals 0. There has to be, right? If you cross from positive to negative, somewhere you cross the x-axis and you get that. All right. So again, that's just some theory that comes in later in math, and so it's worth mentioning here. But good stuff. Anyway, that's graphing polynomials. If you have any questions, bring it up in class, and we will take a look at it. Thanks. Have a great day.